よっしゃ、2時まで終えましょう。
All of us teaching us about science, so thank you, Andy. So this question, are we alone? I think it's a profound question. People have been asking it for a few 100,000 years, and this may be a kind of special time, a special generation where we might have a chance of answering this question in your lifetime. So we should start thinking about what the possible scenarios are and how it might affect us and our civilization. I think the answer to the question is profound either way. If we find out that the universe is teeming with life and other civilizations, we could get on the galactic internet. There may be some civilizations that are billions of years ahead of us. You know, our sun is about 5 billion years old. Some stars are 10 billion years old, so we're kind of middle age. So there could be very advanced civilizations out there. We could learn what's in our future. Studies called the archaeology of the future. That we could learn from advanced civilizations how they got through their bottleneck when they were killing each other, when they had nuclear weapons, biological weapons, chemical weapons. Donald Trump. How did they get through that? But I think it's also profound the other way. What if we find out that we are alone? I think that's very interesting. And it means if we're alone, that means life is incredibly precious, and we better take really good care of life on this planet. Okay, so how are we going to answer this question? One possibility is the theoretical approach. This is called the Drake equation, and you can just calculate the number of civilizations in the Milky Way galaxy, and all you have to do is multiply all these things together, and you know how many civilizations in the galaxy. So the problem with this theoretical approach is that we don't have any idea what any of these numbers are. So it's a way of taking a big question, are we alone, and breaking it up into a lot of smaller questions, but also very difficult questions about how many planets are there. So the first part of the equation is about stars and planets. As you go further down the equation, it gets harder and harder to answer the question. We're starting to know about planets in our galaxy. The next thing about this in the equation is how many of those planets have the right environment. This little E is for environment. Like how many of them are we call Goldilocks planets, the right temperature where you might have liquid water, not too far away from their star where it's too cold or too close where it's too hot, the right chemicals. Then the next thing, this M is for life. If you have a good planet, a Goldilocks planet, how often does life get started? We really don't know how often that happens. It happens very quickly on Earth, but that doesn't mean necessarily happens quickly in other places. The next thing is even more unknown. If you get life, this I is for intelligence. So if you get life started on a planet, how often do you get intelligence? That happened a few times here on Earth, and they have in other places we don't know. The next thing is the C is for communication. If you have intelligence, do they develop communication technologies? Do they have lasers or radio or radar, some way that we can detect their presence? And then the last factor is even more unknown. How long do they live? L is for longevity. So I mentioned that our stars are a few billion years old. It's going to be around another few billion years. So you can imagine very advanced civilizations that last billions of years. We're just beginning. We're just kind of entering this communicative era where we're just beginning to learn how we might communicate with other civilizations if they're out there. I mentioned one of the factors in the Drake equation is planets. And if you had asked Andy and me 20 years ago, are there planets going around other stars? We said, well, we think so, but we really don't know. This is a very recent discovery. And the reason it took so long to find out the answer to the question, are there planets going around other stars, is because planets are little dinky things. A million Earths could fit inside the sun. And planets don't give off light. And they're right next to this really bright thing. They're next to, it's like looking next to a bright star. It's like looking for a firefly next to a searchlight. So it turned out it was a really hard problem. And only in the last 20 years are we beginning to get a sense of how many planets are out there. And the way they were first found is depicted in this slide. They're found indirectly. You can't see the planet, but when the planet goes around the star gets pulled. The planet pulls on the star a little bit. So here's the planet going around the star, and here's the star kind of wiggling a little bit. And if you see a star wiggling,
谷川連峰が見たい。
this is another way to find planets. This is just a few years old. It's called the Kepler spacecraft. It's a telescope that NASA launched into space. It was built here at Ames Research Center down the road. And this is very hard to see, but this little black dot, if you can see it in front of the star. So what happens when a planet gets in front of the star is the star dims down a little bit. You can't actually see the planet, but you can see the star dimming down if we're lucky enough to get the planet crosses in front of the star. And what Kepler is it's just a camera, and it looked at a few 100,000 stars looking for this dimming. And the dimming tells you that there's a planet going around, especially if it's a periodic dimming. If you see a dim, and then another few years later, you see it again, or a few days later, depending on how long it takes for the planet to go around. And Kepler found a huge number of planets going around their stars, getting in front of their stars, and the stars would dim. And from the little area that Kepler looked at on the sky, and you extrapolate, if the galaxy is the same everywhere, which we think it is, Kepler found about 3,000 planets. That means that there are about 1 trillion planets in the Milky Way galaxy. That's more planets than there are stars. That's 5 times more planets than there are stars. A lot of planets, a lot of places for life. This is all brand new in the last few years. We're learning there's tons of places for life. And the other optimistic thing is that some of these planets are in the Goldilocks zone. You might have seen this in the news just last week or a couple weeks ago. The TRAPPIST-1 system is a dim star, but there's 7 planets going around it, and 3 of them are in that Goldilocks zone. Liquid water. So anyway, there are a lot of places for life. Well, the next question is, what if you have a good planet? Does life get started? And we don't know exactly how that happened, but here's a little picture. We think it might get started in something called the primordial soup, and maybe in a tide pool or something like that. And people have done experiments where they simulate the early conditions on our planet. So when the Earth was just forming, what they put in here was some methane, ammonia, water, hydrogen, and they also put in some sparks to simulate lightning. We know that lightning was around when the Earth was forming. And you don't get gorillas crawling out of this thing, but you do get the basic building blocks of life, the amino acids, things that you and I made of pretty complicated organic molecules. So even though we don't understand the complicated details of how self-replicating molecules, RNA, and maybe DNA, form, we're beginning to understand that process. And as I mentioned, it happened very quickly. On Earth, the Earth cooled down, life popped up. It's a very simple life. And so the fact that it happened fairly quickly on Earth gives us somewhat optimistic that it might happen quickly on other places as well. There may even be life in our own solar system. Just right next to us is a moon going around Jupiter called Europa. And what's exciting about Europa is ice, and the ice is about 30 miles thick, and we'd like to find out if there's something swimming around down there in the warm ocean below the ice. And I go to elementary schools and I talk to the kids about how are we going to get through the ice, because we really don't know how we're going to see if there's something swimming down there. And even in elementary schools, the boys give different answers than the girls. So the boys usually suggest machine guns or bombs. The girls are usually a little more clever. They want to melt their way through with mirrors that focus the sun's radiation onto the ice, or lenses or something like that. But it's interesting that early on there's a difference in how to get through the ice. So there's another moon in our solar system that might make the job a little easier. Maybe we don't need bombs and machine guns. So this is a moon called Enceladus. It's going around Saturn, and it's got the same deal. It's got a liquid ocean. The blue is a liquid ocean, but it's covered with ice. But the nice thing about Enceladus is that there are fissures, cracks in the ice, and there are plumes of water squirting out through the cracks in the ice. It would be very nice to fly a spacecraft through those plumes, and maybe we could detect if there is some biological, some single-cell creatures or something. So we don't maybe have to bomb our way through the ice in Enceladus. So that's a very exciting mission that the Europeans are thinking about, and NASA as well. Okay, so that's a little bit about primitive life, but I want to talk to you about advanced life. We might get in touch with advanced civilizations that have a technology, radio or lasers. And you probably know the field is called SETI, which is the search for terrestrial intelligence. And Andy and I are not the first people to think about SETI. This goes back a few hundred years, maybe a few thousand years, but Gauss, the mathematician 200 years ago, suggested that we get in touch with ET by making a large geometric structure on the planet, a right triangle, maybe 3, 4, 5 miles on a side, a big square of dirt, big square of water, and big square of wheat, and ET would look down with their big telescope and see that we knew about the Pythagorean theorem. And this was a very clever idea at the time. You might laugh right now, but it's a clever idea at the time. But the unfortunate part, this was an idea at the time, but it was not funded. Then von Littron, also a couple hundred, suggested that we get in touch with ET by digging a ditch, a circular ditch 20 miles across, and filling the ditch with kerosene, and then use this match, not to scale, to make a bright circle of light, a circle of fire. And again, it was the same idea. ET would look down and see this bright circle of light. I think they were going to turn the fire on and off, put it out, maybe kind of Morse code. And it was a cool idea. Unfortunately, it met with a kind of similar fate. And the next idea was Charles Crow, almost 200 years ago. He suggested that we get in touch with the Martians by having several mirrors to reflect the sunlight to the Martians. By the way, these are my beautiful art drawings. I was a great art student, as you can tell. So he had several mirrors, one where he lived in Paris, and the others to outline the shape of the Ursa Major. And then the Martians would see these very bright lights from the mirrors reflecting, and maybe they would get in touch. I think you can guess what happened with that project. So the first funded project was to send pornography into space. Some of you might recognize this. This is a plaque on the Pioneer 10 spacecraft. And on this plaque, this was very controversial, by the way, these two people were originally holding hands, and NASA thought that wasn't a good idea because ET think it was one creature, so they don't hold hands anymore. So on the bottom of this plaque is the solar system, and here's the sun and Mercury and Venus and then Earth, and you can see the spacecraft leaving the Earth. And then here's the spacecraft with the same kind of scale as the humans, and then are directions to nearby pulsars so they can find out where we live and come and eat us or do whatever they want. So anyway, that was the first funded SETI project. So one of the big ideas in SETI is that Earthlings send off a lot of radio and television and radar signals out into space. And this is a plot of television power leaving the Earth as a function of time, 1940, 1950, 1960. And you can see the Earth is getting brighter and brighter. This is a logarithmic scale, you know what that is. And we now have been sending television out for about 70 years. The early TV shows I Love Lucy and Ed Sullivan left the Earth 7 years ago have now gotten past about 10,000 stars. And the nearby stars have seen The Simpsons. Luckily, the Donald Trump stuff hasn't gotten to the nearest stars. So we're sending out all this stuff. Radio, FM radio goes right out through the atmosphere at the speed of light. Television, radar signals, GPS navigational signals, all that stuff leaves the Earth. And we've even sent messages intentionally. Almost everything that Earthlings send is this unintentional. The television obviously wasn't meant to go out and go past other planets, but it does. There have been a few intentional messages. These are very controversial. Most people, including Andy and myself, think that it's not a good idea for Earthlings to deliberately transmit messages. We don't know what's out there, and maybe like shouting in a forest, and maybe to think that other civilizations are peaceful and they're all going to live together happily, but we don't know that. The right thing to do, at least for now, because we're an emerging civilization, is just listen to it. What SETI is just passive. We're listening to see what's out there. But some people think it's a good idea to transmit. And this is an example of a message that was sent in the 70s. And we think a good way to communicate, they're not going to speak English, is pictures. And they're probably going to be able to perceive their environment in 2 or 3 dimensions. And this is an example of this message that was sent. And here you can see the solar system with the sun and Mercury and Venus and Earth is tipped toward the person. This is DNA, some amino acids, this telescope. So anyway, it was really meant, I think, as a message more to Earthlings that we're getting in the game here. We're starting to learn how we might communicate and detect other civilizations. We should start thinking about the ramifications. You can imagine if we're sending out signals, then we could also look for signals, which we're doing at Berkeley and at the SETI Institute, and many other groups are looking for these signals. Either we could find an artifact of their technology that wasn't really meant for us, but we could detect maybe something like their television or something, or if we're very lucky, maybe a deliberate signal. Maybe they've seen oxygen in our atmosphere, if they're nearby, they've seen I Love Lucy. A deliberate signal. If they send a deliberate signal, I think it will be pretty easy to decode the message. They'll make it anti-cryptographic. They'll have lots of blank pictures and mathematics. Get some sort of artifact from their civilization. My guess is we'll never quite be able to figure out what they're talking about, but we'll know they're out there, we'll know a little bit about them, but we won't be able to really know much about their civilization. Okay, well, as I mentioned, I'm not the first guy to think about this. The early radio pioneers, Tesla and Marconi, both did SETI searches. They looked for radio signals from ET, and both of them thought that they found radio signals from ET. And there were headlines in the newspapers. It turns out they didn't know this at the time, but they were listening to distant lightning bolts thousands of miles away. And the lightning bolts, when they go through the ionosphere, they turn into these whistler noises up. And they heard these chirping noises, and they thought it was ET, but it would turn out to be distant lightning bolts. But it was an exciting thing at the time. So at Berkeley, as Andy mentioned, we have a thing called the Berkeley SETI Research Center, and there are about 24 people, students in engineering and physics and computer science and astronomy, and professionals, programmers and astronomers working together to try to answer this question: are we alone? We have funding from the Breakthrough Foundation, which is not very far from here, and that's called the Breakthrough Listen Project, which I'll tell you about. We also have some funding from the National Science Foundation and from individual donors, and also some companies that are mostly nearby here who are helping us out by donating equipment and some of the chips and things that we use. We have a lot of different experiments that we're doing, looking for radio signals and also looking for laser signals in infrared and at visible wavelengths. We're trying to cover trying to do a lot of different experiments because it's very hard to predict what ET might be doing. But mostly it's looking for technology. We call them techno-signatures, either the kind of things transmitted by AM or FM radio, or maybe lasers, or we're looking for kind of either artifacts or maybe deliberate kind of signals from their technology. So one of the problems in SETI is that we don't know what frequency ET might be transmitting. We don't know what channel. And what you do is look at as many frequencies as you can, as many channels as you can. In the early days of SETI, we couldn't look at very much of the spectrum of the radio spectrum, and so we had to guess where ET would be transmitting. And we thought a good place to look was this thing called the microwave window, frequencies between about 1 and 10 gigahertz. The universe is very quiet. If you tune your radio in that region of the radio spectrum, you'll hear a kind of static, but it's quite quiet, and so ET wouldn't have to turn their transmitting power. We could detect them relatively easy because it's a quiet place in the microwave window. Now we're branching out a little bit. We're searching in many places, scanning electromagnetic spectrum, not just searching for radio waves, those at radio wavelengths, but also we think lasers might be a good way to communicate. Infrared lasers, there's lots of you can also branch out and do different searches using telescopes, different frequencies. The very first project that we did in SETI at Berkeley was funded by NASA, and NASA requires that you use acronyms. So our first project is called SERENIP, Search for Extraterrestrial Radio Missions from Nearby Developed Intelligent Population. And the very first telescope that we used, it's located in Northern California, near Mount Lassen. It's called the Hat Creek Radio Observatory. It's this dish. This is a radio telescope, radio antenna to look for these signals. We used this in the 70s, and this is about 85 feet across. And while we were using this antenna to look for radio signals from ET, this is what happened to that telescope. So this is the dish. It used to be up here on this pedestal. And so, okay, we said, well, we can't use that antenna anymore, so we went to this telescope. This is a bigger telescope. It's 300 feet across, and I don't know if you can see, but there's a full-size jogger down here. This is in Green Bank, West Virginia. And while we were using this telescope to look for ET, this is what happened to that telescope. And you might ask, why is this happening to Dan and his we were wondering about that, and then the answer, according to the World Weekly News, is that the aliens did not want to be discovered. This is a headline, zapped by hostile space aliens, so they destroyed these two telescopes to keep us from discovering them. So that's an interesting idea. We are testing this zap theory at this telescope. So some of you might recognize this. This is the world's largest radio telescope, although the Chinese are building a bigger one right now. But this thing is in Arecibo, Puerto Rico. It's called the Arecibo Telescope, and it is 1,000 feet across, and it holds about 10 billion bowls of cornflakes, although we haven't actually tried that. So this doesn't look shiny to you, but if you're a radio wave, it's got an aluminum surface, and the radio waves bounce off this mirror, and they're collected at a focus up here. And we've got equipment that's running at this telescope 24 hours a day while astronomers are pointing it to whatever they want to point at, galaxy, stars, or studying all kinds of things. We go along for a ride looking for ET. So we don't usually use this telescope just to ourselves. We don't get the point, we let other people point it, but we don't know where to look anyway. So that works out pretty well. But so far, it's a great book, a great movie. I recommend it if you haven't seen it. And the only difference between that movie and real life is that Jodie Foster finds ET, and we haven't. But that it's a pretty accurate description. Carl Sagan worked in our group for about a year. He took a sabbatical with us, so he's an expert on SETI. So I wanted to tell you about this new project that we're doing that Annie mentioned through the Breakthrough Listen SETI project, and it is spectacular. It's beyond our wildest dreams, and we just launched it about a year ago. We're just getting started on this thing. It's way bigger than anything that we've ever done or anybody's ever done. We expect to spend $100 million over 10 years, $10 million a year. We're starting with 3 telescopes, a couple of radio telescopes I'll show you, and an optical telescope to look for laser signals. The one we're using is at Lake Observatory, which is right near here, about an hour up in Hamilton. Some of you may have been there. If you haven't been there, I recommend. It's a beautiful drive, and they have evenings where you can look through the telescope. So most of the SETI projects that we and other people have done have been done from the northern part of the sky, because that's where most telescopes are. But anyway, this will be a new thing for us, is to look at some of the southern stars and galaxies and other things in the south. And as I mentioned, we're just getting started, and 1,000 galaxies. So it's just project. These are the stars that we've looked at so far. We're now getting started looking in the south. So you see, these stars are in the northern part of the sky, the ones that we've done so far. And we've looked at about a little more than 1,000 stars. The different colors, the different kinds of stars, whether indicating the temperature of the star. Some are hotter than our sun, some are colder than our sun. Anyway, so we're learning how to do this, and it's an ambitious program. This is an example of the data that's coming from the observatory that's looking for laser signals. And that gets our attention. It's a narrow signal at some frequency or some wavelength. That's what you might see from a laser from a distant civilization. And unfortunately, I wish I could tell you we found ET, but we know it's not a laser signal because when you look closely at the CCD image, it's coming in at an angle, and that turned out to be a cosmic ray. So occasionally, the CCDs can detect these cosmic rays coming from other places in the sky. And luckily, when the cosmic rays come in, you can usually figure it out because they come in at some weird angle where you'd expect the laser line to be kind of vertical on the CCD. And so we can tell the difference between these false alarms from cosmic rays. So far, no signals from ET. If you are good at computers or interested in this, there's a lot of data that we are collecting in this new Project to Listen SETI program, and we're trying to make the data available. We've got a big and places where you can look at this data and help us figure out how to analyze it. We've got examples of software that we use, examples of how you read it. We're trying trying to get people, especially people who have some computing skills, are interested in data analysis. We want to get the community involved, not just the scientific community, but I think a lot of people around here in Silicon Valley have a lot of skills that we'd like to hope to get people involved. I want to tell you a little bit about the kind of signals that we look for. So I mentioned that one of the big problems in SETI is we don't know what frequency ET might be broadcasting on. So what this plot is how strong the signals are at different frequencies. So this is frequency number 2,064,191. Frequency, I can't read it, but anyways, 2,264,959. And here, at this frequency, is a strong signal. That's the kind of thing that gets our attention. It's like kind of tuning your radio dial across the spectrum, and you're looking at the signal strength meter, and at some channel, some frequency, the signal goes up. That's what we're seeing here. It's a little different than tuning the radio dial, because what we want to do is listen to many, many channels at once. So this is like having millions of radios on your deck, each one tuned to a different frequency. So you don't have to tune here, then here, then here, like a police scanner, one channel at a time, but you can listen to a whole bunch at once. So it just speeds up the process. Anyway, that's the kind I tell you that was ET, but it was a satellite going over the telescope. And there's a big problem in SETI that we're looking for radios from extraterrestrials, but we find a lot of radio signals from terrestrials that we call radio frequency pollution or radio frequency interference. And these telescopes are usually far away from people, and Green Bank, West Virginia is far away from civilization, but civilization is encroaching, and people have transmitters and cell phones in their pocket. You're not supposed to use cell phones when you're near Green Bank, but people do, or they have wireless or something. Cameras give off radiation. Over. It's getting harder and harder to do SETI from the Earth. We may eventually have to do SETI from the backside of the moon, where the moon would act like a shield from all the radio pollution and television pollution, radar signals coming from the Earth. That will be incredibly expensive if we have to move to the moon to do these kind of experiments. So this may be a kind of unique window in our history where we have the kind of technology. If you want, you don't have to do this, but if you want to participate in SETI Home, an optional thing is to join a team, and there are thousands of teams, primary, junior teams. You can make your own team. You can make the Foothill College team. The teams compete with each other in some friendly ways. Here's Intel has donated 1,300 years, and Microsoft has donated 2,000 years. And this competition has led to some interesting behavior. Some people build these big computers in their basements. They're clusters of very fast computers, so that their names will bubble up near the top of the website. They'll get a lot of credit. And you can go to this website called SETIfarm.org, and you can see these guys, and they're all guys. As far as I can figure out, there are no women that do this. Here's another guy computing with his SETI cluster. I don't know why he's got these bolt cutters. Opposed. anyway, this has been a great project for SETI because it's made the search very powerful and it's got the public involved. And even though we have DT, one of the things I'm happy about is that a lot of kids are running this. So this question, are we alone, is something that a lot of kids are interested in. It touches on all different areas. As you address this question, you can get kids interested in astronomy and evolution, how it's like it started in chemistry and physics. It touches on a lot of different areas. We developed a curriculum with the Lawrence Hall of Science to try to get kids engaged while they participate in SETI Home, thinking about this question, are we alone, and learning about the sciences that it touches on. The SETI Home project led us to kind of branch out and think about not just using your home computer to do SETI, but could you use your home computer to do other kinds of scientific supercomputing projects. And we developed this software, open source software, so that you can now use your home computer projects. You can look for cancer drugs, or HIV drugs, or malaria drugs. You can do global warming research on your home computer. You can find new there, and you can allocate how you want your spare computing cycles to be used. You can say you want 30% of your spare computing time to do SETI and 20% for malaria drugs. You can pick your favorite projects. This is SETI Home. This is climate prediction. This is Gravity Wave, looking for new pulsars. This is something called AstroPulse, looking for fast radio bursts. This is protein folding. And you can participate in the projects that did it. And the idea is kind of the democratization of scientific computing power. And there are a billion kind of computers out there, and a lot of it turns out most of the computing power on the planet is into small computers. It's the computers that you and I own, or into the things that are in your pocket right now. And it's called edge resource aggregation. We get a lot of people participating. You think that the supercomputing is really in these giant centers where there are supercomputers, but that's not true. It's the stuff that you and I own. That project, the volunteer computing, let us also think about using the public to do things that computers are not very good at. Turns out computers are not very good at pattern recognition, things that your eye and brain are good at. Our first project we call Thinking Home. We did a project called Stardust at Home. This was a spacecraft that we worked on with NASA to go out near a comet and scoop up some of the dust in the comet's tail. And we all scooped up some of the dust that was around 4.5 billion years ago when the planets were forming, to see how the planets were forming. And this spacecraft, the Stardust spacecraft, came back, landed. It's a sample return mission, landed in the desert in Utah on a parachute, and we brought the samples back to our lab. And they're little microscopic particles from 4.5 billion years old when the planets were forming. And there are also particles in that aerogel foam in our lab that are from the comet that we threw. And we wanted to find these particles in the aerogel foam, the thing that scooped it up, and then we wanted to figure out what they're made of. And it turned out finding these little microscopic particles in these big sheets of aerogel was a big problem. We thought we would need thousands of students looking through thousands of microscopes for years. What we did is we made millions and millions of photographs on this automated microscope that can move around in different focus depths, and we sent these photographs out to the public. And you can help us find the little dust particles. It's called Stardust at Home. And you do a little training what the particles look like, and then you run this kind of virtual microscope on your home computer. And we had about 70,000 people sign up, and they found particles. We're still running it if you want to participate. Particles that we never would have found if we just did it at Berkeley. And we're beginning to learn from this how the planets form and how these dust particles stuck together, and a little bit about how comets are made and how the tail and the nucleus forms. And this is all due to kind of citizen science. And now there are a lot of citizen science projects, not just our projects, but many different things that you can participate in. I want to get back to SETI for a second. I want to say some of the new things that we're working on. This project is called interplanetary eavesdropping. And the idea is if there are machines or beings on two planets, they might be sending messages back and forth. And now with the Kepler spacecraft, we know exactly when these two planets are in line with Earth. And if there are messages going back and forth between two exoplanets, we can schedule our observations and point and maybe intercept communication going back and forth. Like right now, you know that there are rovers going around on Mars and there's communication between Mars and Earth. Maybe there's something like that in a distant exoplanet, communication going back and forth. We're trying to intercept those kind of messages, scheduling when those two planets are in line. This is the project we're doing at Lick Observatory, not too far from here, looking for laser signals. That's Frank Drake from the Drake Equation and Shelley Wright, who's now a professor at UC San Diego. That's me in my youth and the director of the observatory, Rem Stone. We're also looking for infrared signals. This is a project that was built by Charlie Towns, who invented the laser, got a Nobel Prize at up to 100. And Charlie, when he invented the laser, he thought it would be a good idea that might be a good way to communicate between the stars. And at the time, lasers, when he invented, there were little things like this laser pointer, not very powerful, but now they're big lasers that could easily communicate across the galaxy. So we're trying to follow up on Charlie's idea. Well, we haven't found ET. I'm a little uncomfortable with bragging about SETI spin-offs. It's like NASA saying money because we invented Tang and Velcro. But we haven't found ET, so all I can talk about are kind of what we found on the way, these spin-offs. And we have found some interesting things. So one of the things that we found, it turned out the instruments that we developed for SETI turned out to be very valuable in radio astronomy, and we made a bunch of discoveries, or other people use these instruments to find they come from a billion light years away. We don't really know what's causing them, but we think they're going to be very useful to try to understand the universe. We think we can use these fast radio bursts to the cosmos to measure the density, the baryon density of the cosmos, because they're these extremely bright, powerful pulses, and the way they propagate through the intergalactic medium as they come to us tells us something about what's between us and these distant galaxies. Another thing we found, or actually I shouldn't say we, but the instruments that we developed originally for SETI were used by our colleagues to find a planet made out of solid diamond. My wife is very interested in this discovery. We used the instruments that we developed to make the first maps of the black hole at the center of our galaxy. So these instruments have turned out to be very useful. The most massive pulsar. A lot of new discoveries have been made with the instrumentation we developed. They also, mostly they've been used in astronomy, but recently they've been used in other fields, in medical imaging, and we use the SETI instruments to data out of somebody's brain, and we hope eventually that can be used to control a prosthetic arm with an implant that will, with a radio link, and you can control a prosthetic arm. That's kind of distant research, but we're using the SETI instruments to learn how to get data out of somebody's brain with an embedded array. I want to say a few words about what we're thinking about kind of long-term for future SETI experiments. So one of the things we want to do is use bigger, because the signals are likely to be very weak, and so you need a big telescope. So it turns out China is huge, bigger than Arecibo. It's called the FAST across. The Arecibo telescope is 300 meters. It's made out of thousands of aluminum panels, and they finally finished building the thing, and we are working with them to try to get a SETI experiment there. We're actually going to do a survey where we scan the sky, and while we're kind of raster scanning the sky, we're going to be doing lots of things, looking for new pulsars, making a map of the hydrogen in the galaxy, looking for these new fast radio bursts that we don't understand, and at the same time looking for radio signals from ET. So we're going to do 5 experiments simultaneously, all sharing the sky, scanning the sky together. Another new thing that I'm excited about is instead of one giant dish, we are learning how to build telescopes out of lots of little dishes. And the SETI Institute in Berkeley developed kind of the pioneering prototype of this, where we put So now we're building something in South Africa with 352 dishes. We haven't built this yet. We've got 39 dishes. Each one of them is 14 meters. But this is kind of a new way to build big telescopes. Instead of building them as huge dishes, you make them out of lots of little dishes. You can stamp them out like hot tubs. We think this is kind of the future of radio astronomy. And so we're building this now. We just got funded from the National Science Foundation and from the Gordon and Betty Moore Foundation to build this. We're not building it for SETI specifically. We're building it to understand how the first stars and galaxies formed 10 billion years ago. But we'll also try to do some SETI experiments on this telescope. And that's leading up. That's a prototype for this thing called the Square Kilometer Array, which is a huge international project. That'll probably have 4,000 dishes and will be built over the next decade or so. And we're just starting to get mostly the Europeans and the South Africans and the Australians, a little bit of the US, but that's a grand vision for SETI. International that will be built in Australia and in the desert in South Africa, away from people and their transmitters. So we haven't found signals. There's no evidence of ET yet, but I'm optimistic that if there are signals out there, that this might happen in the near future. And the reason I'm optimistic, so I've been looking for ET for 4 years now, a little longer. The reason I'm optimistic is we're not doing the same experiment that we did 4 years ago. So in the 70s, I built a thing that I was very proud of at the time that had 100 channels. I was in the Homebrew Computer Club with Steve Jobs and Steve Wozniak, and I learned how to build these things. And everybody in that club got rich. Me, because I was interested in using these new computer chips to do SETI. I didn't think about building something that other people could use and I could sell. But anyway, so I built this thing that could listen to 100 channels. I'm very proud of it. And at the time, it seemed like better than anybody else. And then we built 65,000 channels and then 4 million channels, and now we're up to about 100 billion channels. Not because I'm getting started. It's all coming out of Silicon Valley right around here, all these companies. And this Moore's Law has made the instruments more and more powerful, almost by a factor of 2 every year, this geometric increase, an amazing increase in capabilities in computing and SETI. The telescopes are getting better, but mostly it's the computing power. This is a graph of computing power as a function of time, and you can see, right, computers are as smart as a lizard or a guppy. But if this trend keeps going, this exponential trend, it's been going on for a long time. It's an economic law. It's not a physics law, but if it keeps going and people keep investing in Silicon Valley, then computers will be as smart as humans in 2030 or 2040. That's called the singularity. It'll be good for SETI. We'll be able to do much more thorough searches and see if there are these radio or optical signals out there. It might not be good for humanity when computers can start designing themselves and they get faster and faster, but it'll be good for SETI. But we should be careful about what might happen in our future when computers are that smart. Okay, so in the long run, there's some even bolder ideas. One of the ideas, but this is maybe 100 years away, is that you could build a huge telescope if you could use the sun as a lens. So the sun has gravity. Einstein predicted this 100 years ago, that the sun works like a lens and collects the waves, either radio waves or light waves, and they come to a focus. And you could use the sun as a huge telescope, as a gravitational lens. That would be way bigger than anything we've got on this planet. A telescope the size of the sun. Now, there's a problem is that the focus is way out beyond Pluto. You got to put the camera out there. We don't know how to do that, but if we could do that, you could license plates on an extrasolar planet. So don't hold your breath on that. That's for your kids or your kids' kids. Anyway, I'm optimistic that if there are signals out there from other civilizations, either artifacts of their technology or maybe, I doubt this, but maybe they're deliberately sending a signal, but I think artifacts, that may happen in our lifetimes. So I'm optimistic in the long run. I'm optimistic about life out there. I think it would be kind of bizarre if we're the only ones, but we really don't know until we're searching, and I think Earthlings are just learning how to do it. This is a very exciting time where we have a chance of finding out the answer to this question, are we alone? Well, if you've been asleep, I have one slide for you. Here's kind of a summary slide. So, no ET so far, still working on it. So that's kind of the summary of this whole talk, but I'm not done. I got 3 more slides I want to show you. So kind of a fun thing in SETI Home is there are a lot of people that want to help us out, and they have a lot of really cool ideas of how to do this. It's a big open source project, and they write the code and add new features and new ways to look for signals and speed it up, and they get the bugs out of the code, and they send us money. Some people help us, which funds the students and the people that work on it, and they give us equipment. Some people do writing about SETI, or they compose music about SETI, and some people send us haikus and there are thousands of haikus that people send us. But don't worry, I'm not going to read you thousands of haikus. I just want to read you a couple. And this is the first haiku is from Paula Cook at Duke University. Searching for life, answers are revealed about ourselves. And this is the last slide and the last haiku. Dan Seidner, 1 million Earthlings, bounded by optimism, leave their PCs on. So thank you very much. Here, please.
Hi. I just had a question about power, I guess. For the telescopes that we have today, are we able to pick up artifacts equivalent to the power that the Earth is emitting at any reasonable distance?
Yeah, that's a really interesting question. So Earth sends off a lot of different kinds of signals. It turns out that the television signals that we transmit are not very powerful, and they would need a really big telescope, and they would have to be pretty close to detect them. Now, we transmit things that are much more powerful. One of the things that Earthlings transmit are something called BMUs, ballistic missile early warning radar systems. The Russians have these to deliver incoming missiles. The U.S. has them in Alaska to deliver incoming missiles. And these things are a little more powerful because they sweep across the sky, so they're kind of in a fan beam. And those would be easier to detect. We've been sending those for about 50 years. And then the most powerful thing that Earthlings send is that big telescope that I showed you, the Arecibo dish, the biggest telescope on the planet, although China's building a big one, but that thing that's 1,000 feet across, it not only can listen, it's not only just a receiver, but it's got a transmitter. Although it wasn't meant for SETI, it was meant to bounce signals off asteroids and study the atmosphere and planets. But that transmitter could be seen, it's a megawatt transmitter connected to a huge telescope, that could be seen, detected on the other side of the galaxy, that's 100,000 light years away. So if Arecibo sent a message, and then you'd have to wait 100,000 years, it would go across the galaxy. If they had an Arecibo on the other side of the galaxy, they could detect that. But it's not the kind of communication between individuals. It's not like, hi, how's your mom? It's like, here's our Library of Congress, all our music, poetry, literature, medicine, please send us yours. Because these messages to that far take a long time. Thank you.
Follow-up to that question, I guess, is do we lose some of the information in those signals? Do they dissipate?
Yeah. So these signals do get weaker. They never stop. They go out at the speed of light, but they get weaker and weaker as they expand and have to cover a larger volume or area of the sphere. As they get weaker and weaker, they get weaker with the square of the distance. It's the inverse square law. And so the further away you are, the bigger telescope you need, or you have to stare at it longer. But they keep traveling at the speed of light. They can't be recalled. Be careful what you say when you're on TV or radio. I think, remember the movie, there was the government was funding this, and then somebody in the Congress said, well, we can't do that because we know the world is only 6,000 years old. Why are we doing this? And is there any government funding? And the second question, is there any pushback from the anti-science community? So the government funding has been kind of on and off. In 1992, SETI was given the Golden Fleece Award. There was a Senator Proxmire, and then there was a guy, Senator Bryan from Nevada. And at the time, they wanted to say that they were cutting costs. You know, they pointed to expensive toilet seats on aircraft, and they thought SETI, the search for, I think they called it a hunt for little green man or something like that. It was nothing in the NASA budget. It was a penny a person or something or less. But that was an example of something that they thought was frivolous, and the funding went away for a while. So the government funding comes and goes, and we've had pretty good luck getting some modest funding from the National Science Foundation and from NASA. And then there's private funding, and that comes and goes depending on the economy and who's interested. But we're extremely lucky now to have our neighbor who owns a mountain nearby. He is one of the key guys behind the Breakthrough Foundation. They give away these breakthrough prizes, like Nobel Prizes, and their very first science project that they're funding is the Breakthrough Listen SETI program. And now they're starting to fund other science projects as well. You might have heard the Starshot project, trying to get a spacecraft to the nearest star at 20% the speed of light. Very exciting. So they got some they like to fund these very high risk, high reward, ambitious science projects. We're very lucky to kind of struck gold. It's a spectacular new program.
Second question, is any pushback from the anti-science community?
So I think, you guys might know better, but my sense is that the public is excited about this question, are we alone? And most of the public thinks it's good because it's not very expensive, especially less than a penny person, and most people would be happy to have a little bit of their tax money to go for this kind of interesting question. There are a few people that think it's a waste of time. There's a small minority of scientists. Most of the scientists think it's a good idea to do this, to do these kind of searches. But there are a few people that think that life is either unique on this planet or incredibly rare, that the biological processes are just, there's something very unusual that happened on Earth, and we don't really know, but some people think, and sometimes it's a religious motivation. A lot of religious